All right, so started. Now, the next topic we are looking at is what? Elasticity. So if we say an object is elastic, it means that the object can return to its original shape or size after being distorted by an external force. If an external force acts on an object and the external force, after being removed, the object return back to where it was, then that object is said to be what? Elastic. Now pay attention. There are some material we call brittle material. There are some material that are what? Brittle. If I say a material is brittle, what does it mean? They can what? They are objects that they break easily. They break easily before getting to the elastic limits. For example, glass, e.g., glass. So the object that will break easily before getting to the what? Elastic limits. But what of ductile material? Ductile material.
They don't break easily. They
Exactly.
don't break easily.
Exactly. They can be extended beyond that. I can say there are others that can be extended beyond elastic limits. Elastic limits before what? Before breaking. Before breaking. Before breaking, exactly. And they are objects you normally use to, we normally use them like we can draw like that. They are objects that can be drawn into wires. Yes, if you hear the word ductility, objects that are ductile, e.g., copper, they can be drawn into wires. Exactly. That's what we call what? Ductility. Exactly. So that's it. So just as you have said, they cannot break easily. Objects that can break easily, they are brittle, and so on like that. So there's a particular law governing elasticity. That law is called Hooke's law. That law is called what? Hooke's law. That law is called what? Hooke's law. Now, you will get the video and the note, don't worry. So whatever I did not write, you will hear from the notes and so on like that. So let's pay attention. So Hooke's law is telling us that provided that we are not extending elastic limits, because there are sometimes that when you extend elastic limits, the object can get to a point whereby it will not be elastic again. So let us say that we are not overstretching the body. So provided that elastic limit is not exceeded, that is why that we do not exceed the elastic limit. What do you say? The force that we are applying on the elastic object is proportional to the what? Extension. It's proportional to the what? Extension. So this is what we call Hooke's law, proportional to the what? Extension. And whenever this proportionality sign changes to equal to, we introduce a constant K. So we call KE. See, in some textbook, you will see extension as E or X. These two both mean extension. Extension, exactly. Extension. So that K that you are seeing there, is called elastic constant. K is called elastic constant. And the unit is what? Newton per meter. That's force over extension. Newton per meter. So if I make from here, this is the formula. Whenever we are dealing with force extension, this is the formula. So let me help you put it in a frame. So we have one formula here already. Now, everybody, if I make my K from here, F equal to K over E, and KE rather, F equal to KE. I make my K the subject of the formula, and I divide through by E. If I divide through by E, you observe that, you observe that my E will cancel out. Then I'll be having K equal force over extension. And please pay attention. K is a constant. So I'm saying F over E is a constant. So if F over E is a constant, it means that F1 over E1 equal F2 over E2. It means that when a force F1 was acting on the body, the extension produced was E1. And if I change the force and apply another force F2, the extension is what? Is E2. So that is what I have. Please give me a second. Let me take my charger. Something is running down. Come. Give me some second. So let's move on. Let's move on. So this is what we have. You will see where we use all these equations now. So let me just call this equation 1, equation 2. So we have 2 equations like that. Okay. Okay, let us look at a scenario to understand Hooke's law very well. Let's say our original length. Please pay attention to this thing. Let's say the original length of a material is something like, what should I use? L naught. This is the original length now. Please, hope you are following. Please follow it. Follow it very well. It's not hard at all. Let me say the original length of an object is L naught. I've not extended the object at all like this now. And let me now say that I came to extend that object to L1. That is, it was at L naught initially. Then I came to apply a force on it. Then it now changed to what? L1. Let me put some things in word. Let me say when a force F1 was applied, that is, I came to apply force F1. The length now became L1. Let me say the length of this object now before was 3 centimeters. Then what happened? And I came to stretch it again. Then the whole length now becomes 5 centimeters. Now check, it was 3 centimeters. After extending, the whole length becomes 5 centimeters. Who can tell me the extension? Who can tell me the extension?
2 centimeters.
How do you get your 2 centimeters? You said the final length minus the initial length. So I have to use that analogy here too. Before it was at L naught. I came to extend it to L1. Therefore, my first extension here, E1, will be equal to what? L1 minus L naught. That's my first extension. Please keep that somewhere. Let me say another force was applied. Another force F2 was applied. Then the length, let me say another person now that has power, come and drag this thing now, and person extended it to L2. Remember, the initial length is what? L naught. The person extended it to what? L2. So the extension E2 will equal to what? L2 minus L naught. So it means that if I now substitute this and this into equation 2, what do I have? I have F1 over what? My E1 is now L1 minus L naught equal F2 over my E is now L2 minus L. So this equation you have here is like more comprehensive because they're not just giving you a simple question that when the force was this, the extension was no. Don't expect straightforward question that way. But this formula has made it straightforward. Please keep it somewhere. Don't trade it. All right, that is that. About that. Okay, let's go. If you hear the word extension, another word for extension is increase in length. All those English can be interchanged. So let's go. Now pay attention. There are some terms we need to know. We call those terms, I'm coming. We have one of them called tensile stress. Tensile stress. How do we find tensile stress? Everybody, tensile stress, denote as ST. The formula is force over area. The formula is what? Force over area. Good. Force over area. That's F over A. The unit is Newton per meter square. And the area we use here, don't forget, the area we use here is always area of a circle. So pi r square. Or if they give me diameter, use pi d square over 4. Area of a circle when you have radius, when you have what? Diameter. So that's how to find tensile stress. Next is what we call tensile strain. Tensile strain. There are many of these, but the one you want to study are this simple thing, tensile strain. Let me just use ordinary S for that. Tensile strength is what? Extension over length. Extension over length. And extension is a form of length, so the unit is meter. Length is also meter, so meter cancel meter, so strain has no units. Strain is dimensionless, it does not have any units, but stress has units. Good. Stress has what? Stress has units. All right, so this is my formula: strain equal extension over length, and that's that. So there's a particular quantity you have to know again. It is called Young modulus. Young modulus. So what's Young modulus? Sometimes some people represent it as Y. Sometimes some people represent it as E, whichever way. But this is Young modulus. Young modulus, the formula is tensile stress over tensile strain. That is whatever you have here divided by whatever you have here. Let's do that, everybody. So we have force over area divided by extension over length. And in my primary school, I think I was taught this thing. I can still remember force over area divided by extension over length. And whenever divide changes to times, what happens? Our force over area times this one will flip over. So we have what? Length over what? Extension. So therefore, to find our Young modulus, we say FL over AE. FL over AE. That's Young modulus. That's Young modulus. So force, this length, this area, and this is what? Extension. Okay. So pay attention about this stress very well. Stress has a unit, Newton per meter square. Newton per meter square is the unit for pressure. It has the same unit as what? Pressure. And who can now tell me what is the unit of Young modulus? Pay attention. Stress has units. Strain do not have units. So stress has units, strain do not have units. So this Young modulus has the same unit as stress. And the unit of Young modulus is Newton per meter square. Strain don't have any units. So Young modulus has the same unit as stress. So that's that for that. That's that for that. Okay. Now from this Young modulus, okay, from this Young modulus, look at what you have here. I have E equal FL over AE. You see, the formula is simple, but to apply it is problem that we students face, but it's very easy. It's very, so just take note of all this very well. It's very easy. Just look at the formula, and whenever we are solving, everything will become clearer. Everything will become clearer. Good. When it becomes clearer, don't worry. When we are solving, it will become clearer. It will make sense. Okay, pay attention. There are some other type of modulus called bulk modulus, shear modulus, but I won't be treating that one here. That one is a little bit advanced. A little bit advanced. Okay, let's look at this graph. Pay attention. Look at this graph, everybody. So when you get to your advanced, you'll be hearing about bulk modulus, shear modulus, different type of modulus, but I won't be treating that here. So we have our load, or let me say we have our stress, and then this is our extension or strength. So pay attention. You see, Hooke's law will be obeyed. The load and the extension, they are directly proportional. A graph that is directly proportional like this, it will be a straight line graph. It will be a straight line, it will be this way. This is what I call directly proportional. And up to this point is what we call the elastic limit. You see these points, this is what they are looking at here. Hooke's law is obeyed from this point to this point. Hooke's law is obeyed. I want to get that. Hooke's law is obeyed. But what happens if I extend beyond the elastic limit? Then I'll be having something like this. Something like exactly. What are these? Pay attention. This point. We have this point, we have this point, and lastly, we have this last point. This last point is called the breaking point. This is what we call maximum load. And this is what we call yield point. Yield point. This is what we call elastic limits. This is what we call maximum load. And this is what we call breaking point. Now you see this elastic limiter. This elastic limit is that point whereby if the force you are applying goes beyond this point, the elastic material will not return to its original side again. Okay, if you go beyond the elastic limit, the elastic material will not go, will not return to its original shape again. That's what Hooke's law said, provided that the elastic limit is not exceeded. So that's number one. So that's number one. You need to think into, okay? Now you see this yield point. Pay attention. Let me tell you something. You see, as you are exceeding this elastic limit, small like this now, the body, you see, that object will be losing its elasticity, small. It will be losing the elasticity, small. And as you are exceeding this elastic limit, the object will be, exhausting all its elasticity. Now, it will not get to a point called the yield point. You see, at the yield point, the elastic material has lost its elasticity and it has now become what we call plastic. Exactly. That it is the point that was the object has lost all its elasticity and has become what? Plastic. It has lost all its elasticity and has become what? Plastic. Exactly. Now, if I exceed this point, remember, you still exceeded this point and you get to the maximum load. You see, this maximum load that you have here, that is the only maximum extent in which the elastic body can go. Then when you get to the breaking point, that is when the object breaks. What we know as a fracture. That's what the object breaks. And that is it. So if you look at this point OE, that is where Hooke's law is obeyed. But anything beyond that extension E, Hooke's law is not obeyed. So this is the last thing I want to be discussing about, how to find work done. Then we call it a day. So how do we find work done? Everybody pay attention. How do we find work done? So to find the work done, or energy, is average force, average force times extension. Average force times extension. So what's so the formula is half FE. Half FE. The work done is half FE. Another formula you can use, that is, if you apply it with Hooke's law, F equal to KE, this other formula can also change to half KE squared. So this is a formula you can use to find work done. This is another formula. Or you use F squared over 2K. Let me tell you something. All this formula can be proved, but don't let us waste our time on proving. Just get the concept. See, whenever you observe a question whereby you have force and extension, use this. Whenever you have a question whereby you have elastic constant or spring constant, K, use this question. Use this formula. Whenever you are having force and K, they did not give you extension, use this formula. So in our next class, we'll be looking at more stuff, okay? We'll look at more stuff. And then look at this object called catapult. Of course, if you want to shoot a stone from a catapult now that you have a bed, if you observe, you will extend the catapult backward. So if you extend the catapult backward, the elastic potential energy stored in the catapult. Remember that if you pull it backward, you have not shot that stone. At that point, when you put it backward, elastic potential energy is stored in the catapult. Then, if you release it, it will be converted into kinetic energy of the stone. The stone will start moving. Just imagine that in your brain. So let us now look at something. So what's elastic potential energy? Any of this formula that I see here for work done. I can say half Fe, any of the formula that I see here, equal to what we use to find kinetic energy, half mv squared. So this will be the mass of the stone and the velocity, and this is where I will stop my class. So you can as well go back, study more by yourself, and then you'll see that you get it better. So that's the end of today's class. So you have any question to ask? You have any questions? So that's the end of today's class, guys. So that's that for that. So take care, guys. Any question? No question, right?
So there's a question.
Okay.
Yes, concerning these young models
Okay.
that we derived the last equation.
Okay.
I'm somehow confused. Like we didn't cross multiply. We just went direct to get E is equal to FL over EA.
Okay. Yeah, pay attention. So for you, just pay attention. Okay, see what we have. We have that Young modulus equal tensile stress over tensile strain. So stress is force divided by area. Strain is extension over length. So if you have something like this, just pay attention. What I'm having here is force over area. Put it here. You see this guy that I see here? It means divided by. Then see what you have there is extension over length. So whenever dividing these two times, you'll be having F over A. This will become times length over extension. So this one is not cross multiply. This one just be multiply. I think that multiply this and this together, I'll have FL.
Okay.
Then you just multiply this and this together, I have AE. That's it. Do you get? That's how we multiply. This is not cross multiply. This is just normal multiplication. So this multiply this multiply this. Is that clear?
Yes, sir. Thank you.
All right. So we call it a day, guys. So you can leave the class now. Thanks for attending. Thanks for your attentiveness. So bye. So you can leave the class for you.